Hey, what's up guys? This is Dr. Vivek Palipuram bringing you the next MIPS Lecturette in ECPE 170. So this Lecturette 2, is going to cover arithmetic instructions and branching instructions. Before we proceed any further, let's recap how we are going to visualize our computers. So we are going to visualize our computers as toddlers that do not know how to speak yet. Slowly and steadily, we are going to teach our computer toddler some instructions so that it can communicate with us. So let's start with arithmetic instructions, and let's start with addition and subtraction. So the addition operation is performed using the add operation or the add opcode that takes in three operands. The first operand is the result, where the result is going to be stored at. Then the next operand is input 1, and the third operand is input 2. So what add instruction does is it adds the contents of input 1 and input 2 without changing these individual operands, and then it places the result back in the result variable. The subtraction is going to work the same way. You need to use the sub opcode, and the three operands are in the same order. Result comes first, then input 1 and input 2. So what this instruction does is it performs input 1 minus input 2 without changing input 1 and input 2, and it places the result back in the result variable. So that's easy, right? Simple add and subtract instructions. So using this slide as motivation, what I would like for you guys to do is try to convert this simple C line to assembly using the add and subtract instructions. What you can do here is pause the video, take a pencil and take a paper and write your solution down. And whenever you're ready, you can unpause the video and we can move on. All right, so I'm wondering if some of you have gotten result or have gotten a solution that looks something like this. Here, first we need to add G and H. So we use a temp variable called temp0 to store the result of G plus H. We use the variable temp1 to store the result I plus J, and then we perform temp0 minus temp1 and place the result back in F, right? Easy. If you have done that, then congratulations, you're now an assembly programming expert. Well, the previous example was just a little bit fake because we made up those variables. We made up temp0, temp1, F, G, H, and I, and J, just like how we do it in C++. When you consider low-level programming, this creation of variables at the programmer's will is actually not allowed. We cannot do that. The problem is that you cannot make up variables in assembly. Instead, you have to use the dedicated spaces that your pertinent assembly language provides. So that's what we need to do. We cannot create our own variables, but instead we have to use the space given by our assembly language. Before we proceed any further and look into the places that our MIPS assembly language offers us to perform these arithmetic instructions, let's recap how your computer system actually looks like. So here is your central processing unit that has its ALU, the arithmetic and logic unit, and surrounding this arithmetic and logic unit, you have multiple registers which are on the CPU itself. Now they are placed very close to the ALU, meaning that any access to these registers will be blazingly fast. It is going to take just one clock cycle in order to access them. A little bit farther away from your ALU, but on chip, is your cache, which is used to store frequently accessed data or the data that will be used again. And then much farther away is your DRAM or your main memory, from wherein you place all of your program's major memory items. It's off chip, it's large, but the access time to it takes more than 100 clock cycles. Now, those students that were in my section, you must recall, or you may recall, a live example that we performed in the class. So your instructor, was the arithmetic and logic unit, or the CPU essentially, and then I had divided the class into memory units and the cache. Specifically, I was standing right here near the whiteboard, and then the front benchers were my cache. They constituted the cache, And much farther away, the backbenchers, there were a lot of students sitting there, and they constituted my main memory. Now, whenever I had to fetch a data from the main memory, I had to make an explicit trip to the main memory if it was not present in the cache. Whatever data that I get, I also get the data that are sitting nearby and place them in the cache, so that the next time I access the data, or next time that I want to access the nearby data, they are already present in the cache. So this is the kind of simulation that we had done in one of our classes. So it's fun to recall that, because I really enjoyed performing that live demonstration. And we found that a processor with a cache, even though it's slower than a processor that can run really very fast, can still outperform it. All right, so as an aside, let me ask you this question. Do we as programmers explicitly manage the cache? You can pause the video here, think about it, and keep your answer in your mind and see whether you got it right or not. And once you're ready, you can unpause the video and we can move on. Well, as it turns out, no. So cache is automatically managed by the hardware. The assembly programmer, they just read and write from the main memory, whereas the cache is automatically managed by the hardware. And as a result, the memory appears to be much faster than it really is, because you're using cache as an intermediate storage. You do not have to make a trip all the way to the main memory to get your data. All right, so in MIPS programming, we are going to be using registers to perform all kinds of operations. For example, arithmetic, branching instructions, and so on and so forth. Everything will be performed using the registers. So let's talk about registers and how they are actually constructed. So if you recall from your knowledge in ECPE 71 digital design, this is how you would actually construct a register. So it is nothing but a collection of just D flip-flops, where each D flip-flop holds a particular bit value. And these D flip-flops are controlled by a clock. So at the rising edge of the clock, whatever data is presented to the D flip-flop, that will be the next state. So if 0 is presented, the next state is going to be 0. If 1 is presented, the next state is going to be 1. That's how your D flip-flops work, and that's how your entire register is constructed using multiple D flip-flops. Now you can also have multiple words here with a little bit more complex circuitry. Well, actually it's not all that complex if you understand the ECPE 71 concepts, but it doesn't really matter for 170, but it's a good refresher for us to see how the registers are actually constructed. So here you have multiple words, word 0, word 1, word 2, word 3. So they are a collection of D flip-flops. And then using signals like write enable and the clock, we control these different words and what are being written into these words. So that's a nice refresher of what you may have seen with respect to registers in ECPE 71. The registers in a MIPS architecture are constructed in the similar manner, but as a programmers, we do not have to really think too much about this internal circuitry. But our goal will be to actively use those registers to perform all the operations. Now remember, all the operations that are performed using registers are blazingly fast. So MIPS is going to offer you 32 integer registers that you can use at your own will. So whatever program that you have to write, you can use those registers the way you see fit. So each of these registers is going to be of size 32 bits. And if you recall from our previous lecturette, a word size in MIPS 32 is equal to 32 bits. So whenever we say a word, that means it's a collection of 32 bits. So these are some of the most commonly used registers that MIPS programmers use. The 0 register that holds the constant value 0. So essentially you can envision a bunch of D flip-flops that are eternally connected to 0, or they are eternally grounded. Then you have the local variables S0 and S7. So there are 8 of them. And then you have temporary registers T0 to T9. So there are 10 of them. So that means all of these registers sum to 19 registers. But where are the rest 32? Well, they're reserved for some other uses. and we are going to learn about them a little bit later, but not just yet. What we are going to do is we are going to actively use these registers to perform all kinds of operations. All right, so let's work on problem number 1 and write a MIPS code that converts or that simulates this C task. So as I mentioned before, you have to actively use the registers to perform all the operations. So let's say that this is your register mapping. Let's say that we are going to use S0 for G, for variable G. We are going to use S1 for H, S2 for I, S3 for J, and S4 for F. What you can do here is pause the video and try to provide a solution for this particular problem. This is problem number 1 in your Canvas quiz. All right, guys, I hope you got the chance to write the solution for problem number 1. Your solution may look something like this. We are going to use the temporary registers to store the temporary values. For example, when we perform the addition G plus H, this result is actually a temporary result. It's not a final result, it's a temporary result. And therefore, by convention, we use temp registers like T0 to T9 to store them. So we perform add of S0 and S1, and we store the temporary result in T0. Similarly, we add S2 and S3. Now S2 and S3 are for I and J respectively, so we add them and store the temporary result in T1. And then finally, we perform T0 minus T1. We subtract these two temporary results and store the final result in S4, which is your variable F. So that's how you're going to convert your C codes to MIPS assembly. You will be actively performing a mapping between the C variables and the registers. You will create some nice comments in your MIPS programs that tell you what kind of register mapping you're going to use. So something like this will be featured as comments inside of your MIPS codes. Some more arithmetic instructions. So let's add one more arithmetic instruction in our computer toddlers vocabulary. And that instruction is the AddI instruction, which stands for AddImmediate. Now this AddImmediate takes in 3 operands. The first operand is the result, which is definitely going to be a register. The next operand is your input 1, which is also a register. But the third operand here can be a positive or a negative number. So for example, if I have to perform I is equal to I plus plus, and let's say that I is represented by register S0, then I can perform add I $S0 $S0, comma 1. Because I plus plus, it actually changes the variable I itself. So here I'm taking I, adding 1 to it, and placing back in I. Similarly, you can do an I minus minus by just changing this to negative 1. So that would be I minus minus, where you are subtracting 1 from I and placing the result back in I. So now we have 3 instructions that our computer can use to communicate with us: add, sub, and AddI. Just three instructions. Okay. So let's take an example of how to use the AddI instruction. So let's say that I have a C line that looks something like this. F is equal to G plus 20. First things first, we need to create a register map. Let's say that S0 represents F, S1 represents G. So I can perform G plus 20 and store the result back in F like this: AddI $S0, $S1, 20. So S1 plus 20 will be placed in S0. Okay, so those were simple arithmetic instructions: add, sub, and AddI. You can perform other complex arithmetic instructions like multiplication and division by using add and subtract as well. Now let's change our focus now to MIPS branching instructions. So let's give some more capabilities to our computer toddler. Let's enable it to make some decisions for us in our programs. Now, the decisions are typically made using the branching instructions. So consider a simple if statement, for example. In C, when you write if-else statements, that's an example of a branching instruction to your computer, because if the condition is true, then you will execute the if portion of the code and you will completely bypass the else portion. But if the if statement is not true, you are going to bypass the if part and execute the else statement. So in this way, you're asking your computer to branch to certain portion of your code depending on whether a condition is true or not. So let's look into some branching instructions that MIPS assembly provides us. We can perform branching based on equality of two registers like this. If register 1 is equal to register 2, if register 1 is equal to register 2, then we are going to branch to this destination. Now, this destination is going to be a label to a particular place inside of your MIPS code, from where your CPU should start processing next. All right, that's what the destination means. Destination is a label. It's a label that is strategically placed inside of your code from where you would like your CPU to start processing next. There are plenty of branching instructions. You can also branch if two registers are not equal. So you would use BNE if register 1 is not equal to register 2, then you branch to destination. You can branch on greater than. So the instruction is BGT followed by reg1, reg2, and destination. Notice how these opcodes are named. They are named quite similarly to what they're actually trying to perform. So let me ask you this question. What will be the branching instruction if register 1 is less than or equal to register 2? Pause your video here and answer this question. What will be the opcode for the instruction that checks whether register 1 is less than or equal to register 2? If so, it branches to a destination. Okay, I hope you got some time to think about it. It's going to be BLE. Branch on less than or equal. Branch on less than or equal to BLE. If register 1 is less than or equal to register 2, then branch to destination. Similarly, you have BGE, BLT, and the previous ones as well. Using these, you can almost convert all kinds of branching instructions in MIPS assembly. And it depends on how you would like to use them. One programmer may use a totally different set of branching instructions, but that's perfectly fine. All right. You can also set registers based on whether or not how two registers compare against each other. So let me actually show you an example here with SLT. So SLT stands for set on less than. And what it essentially does is it compares register 2 and register 3. If register 2 is less than register 3, then reg 1 is going to be set to 1. Otherwise, it is going to be set to 0. So in your programs, you may commonly use flags that are set or reset based on a particular condition. Those flags can be set or reset using the SLT instruction. Then the next instruction is the jump instruction, jump to a destination. We also call it as unconditional jump, meaning that without testing any condition, if this statement were to be encountered, your CPU is going to directly jump to this destination and start processing instructions from there onwards. So there you go, guys. Those were the branching instructions. Now let's talk about code conversion from C to assembly. Now, whenever you're presented a C code that you need to convert to assembly, it's often very useful for us to draw a nice flowchart, something like this. So consider this particular C code, for example. Here in this C code, I'm comparing A and B. So if A is equal to B, then I'm going to execute the if part where I have my equal code. Otherwise, I'm going to execute the not equal code. Either way, after execution, I'm going to continue from after if code onwards. So I can convert this to nice flowchart, which will be quite instructive for me to write my MIPS assembly. So if A is equal to B, if it's true, then I execute the L equal code, and then I go to after if. Otherwise, I execute the not equal code, and I go to after if code. Now, such flowcharts will be quite useful for you. So please try to make sure for initial code conversion, try to use these flowcharts and use them as your guide to write your MIPS assembly. So let's convert the preceding code to MIPS assembly using this flowchart as a guide. So here I'm going to use the BEQ instruction to check if S0 and S1 are equal to each other or not. If this condition is true, then I'm going to branch to the equal code. Now remember, equal here is a user-defined label. You can define label whatever way you want to define them as. Just try to make it consistent though. So if S0 is equal to S1, I'm going to branch to equal code. So it represents this path. I'm going to execute the equal code. When I'm done, I need to jump to done, which is the after if code. Otherwise, if BEQ does not hold true, the branching is not going to take place. Instead, what the processor is going to do is it's going to execute the next instruction that follows the branching instruction. So whenever a branching instruction does not hold true, your processor is going to start executing the following instruction that comes after the branching instruction. So here, if BEQ is not true, the processor is going to execute the not equal code, and then it is going to take this path, after which it needs to jump to after if code. Now, this particular statement is really very important. Just imagine what would happen if this statement were missing. Your processor would have evaluated the not equal code right here, and then it would have proceeded and it would have also evaluated the equal code. So please make sure that you place these unconditional jumps in an appropriate manner. Otherwise, your code is going to execute an incorrect logic. All right, now try to solve problem number 2 on your own. This is problem 2 on Canvas. So use this register mapping here because you cannot declare variables at using your own methodology in MIPS. You have to use certain variables in order to perform operations. So let's say that this is our register mapping. S0 is C, S1 is A, and S2 is B. You can pause your video here and complete the Canvas quiz problem. And once you're ready, you can unpause and we can move on. All right, so let's move on and let's look into an example of a looping statement here. Now again, here I have my while loop while A is not equal to B. If this is true, then I will execute the loop body. And once I'm done, I'll execute the post looping instruction. It's always instructive, as I mentioned before, to convert our C code to a nice flowchart initially. So for some of your beginning problems, try to use the flowchart and use them as guide to write your MIPS code. So look into this flowchart here. If A is not equal to B, then I'm going to go to the post code. Otherwise, I'm going to go to the loop body, I'll execute it, and again, check this condition. That's how your while statement works. Now let's use this flowchart as a guide to write our MIPS code. So your MIPS code is going to look something like this. Let register S0 be for A, register S1 be for B. Okay. Now, there are many methods in which you can convert that while code to MIPS assembly, or rather convert this flowchart to MIPS assembly. This is one of them. So here I have a label start, which I really didn't require, but it's okay. Oh, well, I do require it. My apologies here. And we'll see why. So at start, I compare A and B using the BEQ instruction. If A is equal to B, that means the while statement has evaluated as false, because while was checking if A was not equal to B. Since the while statement has evaluated to false, or if it evaluates to false, then I need to branch to done. So branch if A is equal to B, then I'm going to be done of this while loop. Otherwise, I'm going to execute the next instruction. So if this BQ instruction fails, it means that A is not equal to B. In such a case, I'll go inside the loop body, I'll execute the loop body. And once I execute the loop body, I need to go back to my while statement. So I need to use a jump start, and therefore I do require this start label. And then again, I check the condition, and this will go on and on until BEQ holds true, at which time I'm going to go to my post loop code. Okay. Now let's take a look into this example, MIPS conversion. So here I have a while loop that I need to convert to MIPS assembly, and this loop performs sum is equal to sum plus I, then I minus minus. If I is less than or equal to 0, then break, else continue. And this is my register map. S0 equals to sum and S1 equal to I. What I would like for you guys to do is pause the video here and give it a fair shot with respect to code conversion to MIPS. First, draw a nice flow chart that instructs you how to convert this code to MIPS assembly. And then I'm going to give you my solution. All right, so let me give you my solution here. So first, what I'm going to do is draw a nice flow chart that is going to instruct me how to perform this code conversion. So here I have my while loop, while 1. While 1 means it's an infinite loop because 1 is always true. So I have my while 1 here. So let me write while 1 here. Since it's always true, I'm going to go inside and I'm going to perform sum is equal to sum plus I. Then I am going to reduce I by 1 using I minus minus. And then I'm going to check if I is less than or equal to 0. If yes, then I'm going to go to outside while. Then I'm going to go to outside while. Otherwise, if it is a negatory, if it is a no, then I'm going to go back to my while. So I'm going to convert this flowchart to MIPS assembly now. Let me use another pen here because red pen looks really ominous. Oh, okay. All right. So let's convert this to MIPS assembly. Now carefully notice, guys, what I'll do. I'll use while, if, and outside while as my labels in my MIPS code. So I have while 1. That's the label that I am giving to infinite while loop here, while 1. I need to perform sum is equal to sum plus I. Now the register map was like this. $S0 is sum and $S1 is I. You can specify comments in MIPS assembly using the pound sign. So pound is comments. So the pound sign is comment in MIPS assembly. Okay, so first I need to perform sum is equal to sum plus I. So I can do add $S0, $S0, comma, $S1. So this performs sum is equal to sum plus I. Next, I need to perform I minus minus. So I can do add I, $S1, $S1, comma, -1, which performs I is equal to I minus 1, which essentially is I minus minus. Then I will have my if condition checking. So I'll create a label called if, and here I'm going to check if I is less than or equal to 0 or not. Oops. Okay. So let's see how I can do this. Branch if less than or equal, if I is less than or equal to 0, then I go to outside while. So branch if less than, if I less than or equal, if I is less than or equal to 0, then I branch to outside while, otherwise I jump back to while 1. Otherwise, I'm going to jump back to while 1. And here is my outside while. Always ensure that your labels are defined. If you're using a label, make sure that it is properly defined and placed at a proper manner inside of your MIPS code. So there you go, guys. This is how you can use flowcharts as your vehicle to convert, or your guides to convert your C code to MIPS assembly. Use flowcharts for initial problems, and as you practice more and more, this will become natural to you. You'll start making flowcharts in your own heads and then convert MIPS code, then convert C codes to MIPS assembly. So we have just used arithmetic instructions and branching instruction to convert this code to MIPS assembly. All right, now pause your video and solve problem 3 here, which is also on Canvas. It's a simple for loop. So let me draw the flowchart for this long for loop here for you. So I have my for loop. Sum is initialized to 0, I is initialized to 0. That's fine. Those should have been done before. So here I'll check, I'll check if I is less than 10. If this is a yes, then I'm going to do sum plus equal to I. Then I'm going to increment I by 1, and then I'll go back. If it is a no, then I'll go to outside for. You can convert this flowchart to MIPS assembly, or you can draw your own flowchart and convert that to MIPS assembly. Similarly, I would like for you guys to solve problem number 4 and convert this piece of code to MIPS assembly. Now it's a little bit, I wouldn't say it's completely challenging, but it's a little bit more of a higher complexity now that you have nested looping statements here. So inside of this for loop, you have a while loop that is nested in. So you need to convert this to MIPS assembly. Try to draw a flowchart on your own and convert that to MIPS assembly and give your solution on Canvas page. Okay, so I think it's a good point for me to stop this lecturette right here. So in this lecturette, we taught our toddler computer some new language, some new instructions, and those were arithmetic, comprising add, sub, and addi, and some branching instructions for it to make some decisions. And next, we are going to look into more complex instructions that are going to help your toddler computer to perform even more neat tasks. So we are going to end this lecture right here. Thank you for your patience. And if you have any questions, both Dr. Schaefer and I are just one email away, or you can always use the Slack channel to instantly ask us questions if a complete email is not necessary. So I'm going to end this lecture right here. Thank you guys for listening.